Hello, everyone, and welcome to today's webinar on emerging research on PFAS and biosolids. I am April Thompson, Senior Director for Bloom, which you're going to hear a lot more about momentarily. We do have a packed house and a packed agenda, so I'm going to try to keep my introductions quick and keep this moving along. A few housekeeping items before I introduce our featured speakers, because we do have over 500 people actually registered for this event. We know there's going to be a lot of questions and a good chance we may not make them all through them all in the time allotted. So we ask that you use the Q&A function to submit a question, and please just try to keep those concise to help us get through as many of these as possible. So without further ado, I'd like to introduce today's speakers in order of appearance. First, we're going to hear from Chris Peot. Chris is Director of Resource Recovery for DC Water and Interim President of Blue Drop, which oversees the sales, marketing, and distribution of Bloom. Chris directs an array of projects for Blue Plains wastewater treatment plant, from the Bloom program to renewable energy. Chris began his career in the Los Angeles Bureau of Sanitation, where he worked on biosolids management and water reclamation. A licensed professional engineer, Chris has a BS in Civil and Environmental Engineering from the University of Wisconsin at Madison and an MS in Civil Engineering from California State University. Chris is also a Water Environment Federation Fellow and recipient of the Mid-Atlantic Biosolids Association's 2025 Lifetime Achievement Award. We will next hear from Dr. Ian Pepper, an environmental and microbiologist and Regents Professor of Environmental Science at the University of Arizona. His research has focused on the fate and transport of pathogens in air, water, soils, and municipal wastes. Dr. Pepper has co-authored numerous books and journal articles on environmental microbiology and pollution science, and is a fellow of the American Association for the Advancement of Science, the Soil Science Society of America, and several other notable organizations. He received his PhD in soil microbiology from the Ohio State University, go Buckeyes, MS in soil biochemistry from Ohio State, and a BS in chemistry from the University of Birmingham, Great Britain. And last but not least, we will hear from Dr. Linda Lee, a distinguished professor at Purdue University with a joint appointment between the Colleges of Agriculture and Engineering. She joined Purdue in 1993 with degrees in chemistry, environmental engineering, and a PhD in soil chemistry, contaminant hydrology from the University of Florida. Her research includes chemical fate, water reuse, bioaccumulation, and contaminant remediation and management strategies, with PFAS challenges driving much of her research for the last 2 decades. Dr. Lee has published almost 200 publications, with most in top-tier environmental journals. Chris, the floor is yours.
Thank you. Really appreciate it. Thanks for setting this up, April. I am, as April mentioned, Chris Peot. I'm an engineer here at DC Water, Director of Resource Recovery. I want to talk a little bit about Bloom, because I'm not sure everybody on the webinar is familiar with biosolids. Bloom is our branded biosolids product. It is a specialty fertilizer and a soil amendment that we sell in the region. And then I want to talk a little bit about PFAS, setting up the talks that are going to follow, Dr. Pepper and Dr. Lee. They're doing some really important work. We are as concerned about anybody about PFAS in our environment. And we want to strike a balance so that we can continue to use this valuable asset that comes out of our treatment plant. Really, we want to try and make a distinction between municipal biosolids, which have sort of societal background levels of these chemicals, similar to what we have in our bodies already, and industrially impacted biosolids. So with that, I'm going to zip through a few slides. This is really just an intro. Let's see here. So the role of a water resource recovery facility, we don't really even refer to ourselves as wastewater treatment plants anymore, but rather as resource recovery facilities, is to help protect the environment by keeping, in our case, carbon and nitrogen out of the Chesapeake Bay, preventing algae blooms, preventing eutrophication and dead zones. So it's, those are pollutants out in the bay, but carbon is energy and nutrients are fertilizer. So 10 years ago, we started up this process, these digesters, which are pretty conventional technology, but they were preceded by thermal hydrolysis, which is a high heat, high pressure system that does two things. One, it kills all the pathogens. It's 160 degrees centigrade, so it's well above pasteurization, but it also prepares the solids for the hungry microbes in the digesters, which allows them the microbes in the digesters, whose job it is in nature to convert organic matter to methane, to convert more of the solids into methane, which means we get more green energy out of it. We produce about 7 or 8 megawatts of clean, green, renewable power and recover the heat off the turbines to heat up the thermal hydrolysis system. But as a result, we have very, very stable and low odor product coming out of the bottom because a lot of the organic matter has been converted to methane. And we do not, in DC anyways, we don't have very much industrial input. It's mostly government and businesses. 97% of our wastewater is received from non-industrial sources. That's not the case in every city. So what comes out of the bottom of the digesters is our beautiful Bloom product. I know it's my baby, but I tell everybody I think it's the most beautiful biosolids on the planet. It looks just like rich Iowa topsoil. It provides water holding capacity, and has tremendous amounts of micro and macro nutrients. And it's really good. If anybody's interested, you should check out our website that is maintained largely by April. Has tons of information, testimonials. We are very transparent about our testing, so we have test results on there for all of our nutrients and things, but also for PFAS. So check it out. It's very, very informative, and thousands of pretty pictures. So Bloom, as I mentioned, it's slow release fertilizer and soil amendment with benefits similar to compost. We manufacture it using this world-class technology. The thermal hydrolysis, which is in the upper left there, is a Norwegian technology. Ours was the first installation of it in North America and the largest one in the world. Others are now following suit. There's probably a dozen either operating in construction or in planning in the US now. We're very proud of that. And we achieved through this process EPA's highest ranking Class A exceptional quality, which means that we can sell it to the public because it's low in pathogens. And only 11% of the biosolids in the entire US have this rating and are marketed to the public. The value in the biosolids, of course, are in the organic matter that we're returning back to the earth from which it came. That's kind of the way the earth is supposed to work. Grow something, put it back on the soil, turn it into more soil. There's nitrogen and other macronutrients, plus all kinds of very, very important micronutrients that you don't get in synthetic fertilizers. Beneficial microbes get returned to the soil. These are all naturally occurring, coming out of our digesters. And we provide drought resistance for the farmers that use the material. I have a whole presentation on this, and I'm short on time, so I'm not going to explain it, but we've did a 3-year study, and we proved beyond a shadow of a doubt that the phenomenon is real. If you use our biosolids, farmers can get through stressful conditions like drought. We have several different Bloom products. Our fresh Bloom is what comes straight off the belt, and we sell that to farmers and to soil blenders. We also make some blends, which are used in various different areas. The blends are ideal for commercial and residential landscaping and gardens. These are just very few of the many, many beautiful photos that we have on our website. DC Water employees get the material for free, which is great. All we ask is that they take pictures of their beautiful plants afterwards. So we've got tons of information from customers and from employees and from other users. We have done a lot of athletic fields with our biosolids. This is one of our blends that we brought out to Shirley Chisholm Elementary. And I know this field very well because I live on Capitol Hill. This is in Southeast DC, right on the edge of Capitol Hill. And my kids played soccer on this field, and it was terrible. It was pitted. They couldn't get any grass to grow on it or anything. So we worked with Sports on the Hill, brought a bunch of parents out with their kids. We brought the material out. We spread it out all over the site, and it is now beautiful. It is a gem in the Sports on the Hill soccer field crown. So on to PFAS. Of course, that's what we're here to talk about. since you're on this webinar, you're probably familiar with this. I'm just going to zip through it. But it is, PFAS is in so many different products that we use every day in our homes. And it's in, food packaging and in food wrap, and it ends up in food, and we eat the food, and it ends up in our bloodstream. We use all these products, and then we have to figure out what to do with them. Paper and plastic wastes, which have a lot of those have PFAS in them. It's in plastic to make it stronger and to make it slick. Those go to the landfill or to incinerators, and in the if they go to the landfill, there's leachate, which gets returned to the wastewater treatment plant, so we have to treat it. And incinerators, they burn the trash, but we're finding that in some cases the temperatures aren't high enough to destroy the PFAS, and it ends up in the exhaust and in the atmosphere. And it comes down in rain. I've got a slide about that later. We've got products that we use in our homes that enter the sewers through our sinks, our laundry, and through industry as well, not just in our homes. And human feces and urine can contain PFAS from daily exposure to products and food packaging and dust. And although we know that the highest concentrations, even in DC, come from industrial sources, and we can limit those, the greatest mass comes from our residential area. We've calculated, we've gone up, sampled upstream in the sewers, and found out that 95% of it is coming from residential areas. So there's all kinds of studies on household dust too. There's two that I'm going to cite in this study. This is one that was done in Sweden, and it looked at a whole bunch of different countries. The US was not included in it, but I'm comparing, Canada. In Canada, it's the second bar from the left. The PFAS in Canadian household dust was about 100 parts per billion, and PFOA was about 50 parts per billion. I'm showing these because eventually I'm going to show another one that shows sort of relative concentrations, just to show how low they are in the biosolids. They're incredibly low, and really at those sort of societal background levels. And it's in rainfall. I haven't done an extensive study on this, but I think it's safe to assume that at least some of that is coming from incinerators, that burn trash and it ends up in the atmosphere. And I actually looked at these studies, and there's a bar on here for Maryland. It's about a third of the way from the left. Maryland 99, I think it is a sample of precipitation that came down in Maryland. We also have data from Virginia, and we do have PFAS in our bloom. It's about 13 to 15 parts per billion. And if we apply that at agronomic rates, it deposits about 14 milligrams of PFAS per acre per year on our farmland. And I was just curious how that compared to rainfall. And I looked at these numbers, and I make some assumptions based on this. But if we assume that bar has 2 parts per trillion of PFAS in it, which is not it's not unreasonable. And you do the calculation based on average annual rainfall in Maryland, a farm is going to receive about 12 milligrams per acre per year from rainfall. So what's in the biosolids is similar to what comes down in the rain. And you guys can probably do this math, but I did it anyways. Just if you look at the mass that goes down, it is about 1/3 the mass of a drop of water. So 1/3 of a drop of water in mass in PFAS gets spread across an entire acre of farmland. So very small. New York has looked and done a survey at their soils, and these are not farm soils that have received biosolids. These are soils that are quote unquote undisturbed. So it's away from roadways, it's in forests, it's in areas that would not have received any anthropogenic contributions that we know of, not intentionally anyways. And they found that anything up to about 3 parts per billion is considered to be background levels. Now, they did not go so far as to figure out where that came from, but it's most likely coming down with the rain. It would be interesting to do a study to look at plumes from incinerators and see if there are higher levels. But this just came out, so it's really interesting. And the result of all this exposure, we have in our own bloodstream, the average American has PFAS chemicals in their bloodstream. And I would like to point out that we're doing something right, because 20 years ago, we were very high, and there was a ban on, I think it was in Teflon pans. And because of that, it has dropped considerably, and now it's leveling out. But these levels are roughly what we have in our plume biosolids as well. So I promised you some relative concentrations. These are concentrations in other products that we have. And if you look at the PFAS and PFOA in bloom, it is way on the bottom of this list. And I did not put on the slide all the references, but we have them for these, if you'd like. Thousands of times higher in things that we eat, things that we put on our body so that our mascara doesn't run, a lot of different things. And we recently looked at our blends too, because we thought, oh, it'd be interesting to see where we are with blends. And we sampled some leaf compost. This isn't our product, but a leaf compost. And then our sandy blend, a food compost that wasn't ours either, and a woody blend, and then compared it to a typical industrially impacted biosolids. And then that dotted line on there, that red dotted line, is the average American PFOS level in blood serum. So it is, again, comparable in these products to what's already in our bloodstream. Not suggesting it's great, but I think that there are bigger fish to fry than biosolids. So then I wanted to show this. This is my last slide, and this uses some data that Ian, Dr. Pepper, collected in Arizona. So these first 3 bars, which you can barely see, are farmland that has received 5 to 10 years of applications of typical municipal biosolids. The second one is 12 to 20 years of application. The third one is local soils that never received any biosolids, and they are all statistically almost identical in PFAS levels. And the one on the right is Songbird Farm in Maine. So that is one of the farms that has been the focus of this entire controversy, and it received paper mill sludge. And we don't really know what the levels were in the paper mill sludge because it went down in the 80s, but the soil is incredibly contaminated. So one of my messages here is we really, really need to make a distinction between municipal biosolids, which have background levels, societal levels, and industrially impacted biosolids. Clearly, we need to do something about those. I could go on and on and on, but I think I am done with my time. I think Ian's up next. Thank you.
Thank you, Chris.
Yes, I will stop sharing.
I'm hitting the share button and nothing's happening, April.
Okay. Maybe stop sharing and try again. Maybe it took a minute for Chris's to be taken down on your end. If we have trouble, I can always share. I've got your slides and I can share for you.
Yeah, it's just not working.
Okay, let me just pull your slides
Pull
up
them
and
up.
I can run them for you.
Okay. I have trouble with Teams every time.
That's okay.
Getting close.
I'm hearing some background noise too. I'm not sure who that is. It's like a fan, maybe.
That might be my computer that does have a very nice noisy fan. I will mute myself in just a second here. Okay. All right.
Is that the full screen?
Yep. Are you able to see
Okay,
that? So you
good to
can
go.
tell me when to switch slides?
Sure. Yeah.
All right. Take it away.
Well, good morning, everyone, and greetings from Tucson, Arizona. And greetings also from the West Center. So it's my pleasure today to give you an update on the National Collaborative PFAS study, which has attracted a lot of interest nationally. Next slide. So with respect to PFAS and biosolids, biosolids always has some PFAS in it. And so if you look at the potential exposure to PFAS from biosolids, direct exposure, the very minimal risk because most people don't allow their kids to play on a land-applied field. So the concern is with indirect exposure. Two sources. One is drinking water contaminated with PFAS after it's leached from the land-applied biosolids through soil, through the Purdue zone, into groundwater, and then subsequently used as a potable supply of water. The other indirect source is plant material from crops grown on land application plots. And so in this national study, we're looking at both of these indirect exposure routes. Next one, please. So concern over PFAS has ramped up over the past 5 or 6 years. Locally in Tucson, Pima County, there was a moratorium on land application in 2020, which resulted in us doing a local study on land application plots where we knew the lifetime loading rates. And this is where we gained our expertise in sampling soils for PFAS. We had Maine banning land application in 2022, Connecticut in 2024, and now people are worried about a national ban. And lo and behold, just earlier this morning, I received an email telling me that a proposal is now going before the Arizona state legislature to ban land application, particularly you're not allowed to use any fertilizer, biosolid, or sewage sludge containing any PFAS. And the proposed ban is to go into effect January 2028. So we have time to look at this. But I think there's about a dozen or so states nationally where the legislatures are looking at land application as to whether it should continue. So it's a real issue. Next one. So this concern gave rise to the National Collaborative Project, in which we wish to evaluate whether or not land application of biosolids is a significant public health route of exposure to PFAS. Next one. So our two specific objectives looked at the two indirect sources of exposure. First, at land application sites nationally, we measured incidence and mobility of PFAS at land application plots following long-term land application. We did this by taking soil samples at the surface and then the subsurface to assess mobility. And then in phase 2, we now knew the concentrations of the PFAS in plots all over the country. And we were now growing crops on these sites. And I'll get into that later in the presentation. But in phase 2, then we're looking at paired data sets of soil and plant PFAS concentrations. Next one. So this was a nice idea, but I had no grant, no money for research, but people really liked the idea. So I started giving a series of talks nationally, and lo and behold, the project was funded by a number of wastewater utilities, private sector companies, and nonprofit organizations. Hundreds of thousands of dollars. Next one. And these are the funding organizations. Very impressive list from all over the country. Significant contributions from Bay Area Biosolids Coalition, Northwest Biosolids, Metropolitan Washington Council of Governments, including Blue Plains, LA Sanitation Districts, Orange County, Great Lakes Authority. So the response to the need for the research was fantastic. Next one. So this is a unique project in a couple of ways. One, it's truly national in scope. We have sites where we've collected samples all over the country with different soils, different depths to groundwater, different climates, and including irrigated and non-irrigated sites. Secondly, and this is a little counterintuitive, the research methodology at each site was identical, allowing for a direct comparison of data and a national set of real-world field data. And we achieved this by actually making an 18-minute video of how to collect soil samples for PFAS analysis in the field. And it's 18 minutes, and if anyone has trouble going to sleep at night, I can send you the video and it'll take care of your problem. So having this national set of data allows us then to now get into model development, risk assessment, and two important points. One, we're looking at municipal biosolids, not industrially contaminated. And secondly, all of the samples were sent to the University of Arizona where they were processed and analyzed. Next one. So at each site, we actually took 27 soil samples. So at each site, there were 3 plots, a control plot with no land application, and then 2 land application plots with lower and higher rates of biosolids. So within each plot, we took 3 cores to get an estimate of the range of concentrations across that plot. And from each core, we took soil samples of 1 foot, 3 foot, and 6 foot. So that's 3 plots times 3 cores per plot times 3 samples per core. That's your 27 soil samples. Next one. These are the PFAS analytes which we looked at. You're not supposed to read all of these, but the idea is to show you that we were looking at a wide variety of PFAS analytes, including, of course, PFAS and PFOA, which are the 2 most infamous PFAS analytes. And we used EPA method 1633 for analysis. Next one. So this is a map showing you the states where we had sites, land application plots, and collected our soil samples. It's a pretty good spread across the country. And if you're in any doubt, I can assure you that having this 23 sites in 17 states and having all the samples come to Arizona, it'll keep you busy, okay? Next one. Just to show you the loading rates, 2 tables on this at the different sites. The pertinent points are, first of all, the loading rates are different. These are the lower ones. Also that we have Class A and Class B biosolids, and we have land application going all the way back to the 1980s. So it's a pretty good test of the influence of land application over many years with many applications. Next one. These are the higher biosolid rates, and you can see we're now all the way up to 92 dry tons per acre. And again, going back to the 1980s, and again, Class A and Class B. Next one. Also, we looked at the soil texture at the surface in all the sites, and the darker the color, the sandier the soil. But the important point here is that the textures at the sites went all the way from a clay, as in site 6, to a sand in site 5. So we had a complete range of different soil textures, and again, illustrating that it's a pretty good test of incidence in sites, land application sites with different soils. Next one. So here's the status of phase 1 then. We've completed the sampling, 23 sites in 17 states. We've completed the PFAS analysis. We've completed the attenuation study. We're almost complete with the soil organic carbon analysis. That'll be done by the end of probably a couple of weeks. And from that, we'll be calculating soil screening levels in which we can quantitatively assess the potential for contamination of groundwater by looking at the soil screening levels compared to the actual soil concentrations of each analyte. And we'll do that for every soil sample that we've taken. And so there'll be several ways to analyze that data and additional manuscripts coming out. The one first peer review paper came out earlier this month, and I'll give you the citation in a minute here, so you can look at that if you're interested. Next one. Just going to give you a little snippet of data, and I'll start by mentioning at the end of this slide deck, I have 3 slides which give you a massive amount of data on incidence, including the mean values of soil concentrations for all analytes, the median values, the maximum values. So you can look at that at your leisure if you're interested. Obviously, I don't have time to go through all of that data in this presentation, but here we've got some select analytes that are important, particularly PFOA and PFOS, which are the 2 analytes that EPA chose to regulate for drinking water with a maximum contaminant level of 4 parts per trillion. So C is control here, L is low biosolids, H is high biosolids. And if you look at the soil means for PFOA, they're modest values. And in particular, there's not that much difference between the control soil values and the low biosolids values. If you look at PFHXS and PFNA, those concentrations are very low. And interestingly, of these 4 analytes, nationally, we found that PFOA was the most ubiquitous. You could find it most frequently, but PFAS was the analyte that we found in the greatest magnitude or highest soil concentration, probably due to its use in firefighting foams. If you look at the mean and the medians, the median values are excellent. They're all less than a part per billion. And the median values are always lower than the mean values because the mean values can be skewed by occasional high values. And you can see the soil maximum concentrations that we found on the right there, CL and H. And what's interesting is that even in the control, we're finding significant PFAS, and look at PFAS, almost 21 parts per billion. Where that's coming from, we don't know, because again, these are sites that have been monitored now for almost 50 years. Next one. Looking at attenuation, particularly looking at the influence of chain length on attenuation. So you can see here shorter chain, intermediate chain, and longer chain. And the story is when PFAS and biosolids are applied to soil, the PFAS can be absorbed by soil colloids, soil clay content, organic matter, and also significantly at air-water interfaces. So as the PFAS goes through the soil, some of it gets absorbed, meaning the concentration beneath it is lower and the concentrations available for groundwater contamination are lower. And essentially what you see here is the longer chain have the highest rate of attenuation, 85, 84, 86, 100%. And if you look at the overall mean values of attenuation for all analytes over all chains, it's 50% at 3 feet and 72% at 6 feet. And that's great news in terms of soil's ability to protect groundwater. Next one. We also looked at recent samples of biosolids, which of course the concentrations have changed now relative to 20 years ago. But if you look here, the 2 slides on this, these are half of the sites. And the quality of the biosolids with respect to PFAS analytes is really excellent. The values are very low. We have 2 problem sites there, site 7 and site 12, highlighted with yellow. PFAS and PFOA, these would not meet the Michigan Eagle standards for land application. And in particular, Site 7 had these very high values. So we arranged a conference call with the personnel at that site. And lo and behold, there was a direct line from the landfill pumping landfill leachate into the wastewater of the utility. So that's probably the major factor in those high concentrations and illustrates how industrial contamination will jack up those biosolid values. Next one. So these are the, oops, you've gone to back one. These are the other sites, and you can see here site 19 also did not meet the Michigan Eagle standards for land application. But all in all, that's a good report card for the quality of biosolids nationally that is being land applied. Next one. No, other way. Oh, next one. We're in a do loop. No, you're going backwards. One more. Okay, the first peer review manuscript, that's what I'm after. Back one. There you go. So this is the paper. There's the citation, Science of the Total Environment, and you can get that citation down later. The highlights of this paper are, first, it's the largest US database of soil PFAS concentrations in land application plots. Median PFAS surface soil concentrations of all PFAS analytes were all less than a part per billion, nanogram per gram. Significant attenuation of soil PFAS occurred with increased soil depth, with 72% attenuation at 6 feet, and 80% of the land application sites met Eagle standards. Although recall, this was a single sample, so more work needed there. And overall, I think it's fair to say that the low PFAS concentrations in soil would be expected to reduce the potential for groundwater contamination. Next one. So phase 2. So we've now established these sites where we know the soil PFAS concentrations. Now we're establishing a national network of crop uptake on the sites from phase 1 with the known soil PFAS concentrations. We're looking at multiple crop types, which I'll show you in a minute. And there's also the same crop at multiple locations so that we can see the influence of different soils and climates on particular crops. And again, going to generate paired data sets of soil and crop PFAS concentrations, and it's truly national in scope. Next one. So the crops are planted. We have plant samples now from 14 of the 21 sites, and we'll be getting the remainder here in the next 2 or 3 months. PFAS analysis is underway. We expect to get the first results in February. Prior to doing the analysis of plant material, I actually did a pilot study looking at 3 different methods of analysis for plant PFAS material. So we should then be wrapping all of this up later this year. Next one. This is one of my favorite slides. So 21 sites in 15 states. Arkansas, Arizona, California, Colorado, Florida, Illinois, Kansas, Maine, Minnesota, North Carolina, New Jersey, Ohio, Pennsylvania, Virginia, Washington. Crops: alfalfa, barley, corn, cotton, grasses, oats, peas, rye, soybeans, triticale, and wheat. Same crops in multiple state locations: corn, oats, soybeans, and wheat. And we're also looking at concentrations in different plant parts. So for example, with corn, we look at the grain and we look at the stova. So I think I'm just about finished here. Next one. There are questions, and just go one more and give them an example of the data that's there available. So we got 3 slides there with control, low biosolids and high biosolids with all of the data if you're interested. So with that, I will close.
Super, thank you so much. Linda, over to you. And just a reminder to everyone, and I will note there are folks who have had difficulty joining. I know a lot of people had to instead join by phone. We apologize for any challenges there. Hopefully, folks are still able to type in questions to the Q&A. If you're dialing in via phone and you're having trouble with that somehow, you can, if you email bloom@bloomsoil.com a question, I can try to pick it up from there. Apologies for that. And over to you, Linda.
Thank you, Ian. I'll have to go quick because Ian used up more time than he planned. So I'm just going to start out by telling you up front I have 10 sites in 4 different states, and I'm just going to show you some examples. PFAS from soil to groundwater. Because long chain persists in the surface soils, the whole surface, the upper soil profile, but including surface soils, they are more prone to being available for plant uptake longer and run off into water bodies. You'll see that applications of new biosolids have very small PFAS signatures. Sorbent, I'm going to show you some examples of sorbent mitigation strategies in the greenhouse and then compare it to what we have so far in the field, and we'll see that it's going to be very tricky to predict and achieve the outcomes we want from sorbent mitigation on PFAS plant uptake. You'll see that we can, if you have a PFAS contaminated field, you can control PFAS uptake into the food system by choosing your crops wisely, selecting your harvests at different times as we wait for future more comprehensive mitigation strategies. And as I'll point out, which I feel like Chris also pointed out and Ian a little bit, our biggest issue is our legacy PFAS, which are not in our biosolids very much anymore, and our industrially impacted biosolids, and those are even legacy. So I just want to do one prep slide to make sure you can understand fate and transport. When we talk about PFAS, it is an alphabet soup even for a chemist. So we can think about them as short chain, long chain, precursors, and intermediates. We also can think about, we have the carboxylates like PFOA has a CO2 group at the end. We can have the sulfonates, which we call PFSAs like PFOS, and they have a sulfonate group. Those together we call the perfluoroalkyl acids, and those are the persistent ones. Those are the ones that once they get to that point, they persist, and we really don't have very viable strategies to break them down naturally. The thing with short and long chain, shorter chain are more mobile, so they travel through the soil quickly. They're less bioaccumulative into animals and humans. They do have a higher transpiration into plants if they're present in the root zone, but they do leach more rapidly, so it's a competition. The longer chains, like the ones we're familiar with, infamous PFOS and PFOA, they're not as mobile, they're more bioaccumulative, they biomagnify across the food chain, and they have much longer half-lives in humans. This is why they're a problem, coupled to the fact that they're persistent and linked to adverse effects. When we talk about precursors or intermediates, these are compounds before the perfluoroalkyl acids, and they could have been the precursors or the intermediates or the PFAAs could have been the initial PFAS in a product or a commercial process. But a lot of times they are not these final terminal end products. They're things that are prior to that. And that's, I'll give DuPont's synthesis process. They have this linkage here that has no fluorines, and it's very easy for microbes to attack, and it leads to multiple PFCAs like PFOA and shorter chain. So in this case, 6,2-dipap can lead to a lot of C6 carboxylates and shorter. And so you can have one molecule lead to several molecules. And the one molecule that it started with is not even on the EPA 40 list. Another example is the 3M derived process. Down, but only to one final persistent product, which is PFOS, one chain link. So that's important to know in your transformation, in your transport.
Linda, we're having some issues with your connection, I think. I was going to suggest maybe if you just turn off your camera, sometimes that can help with bandwidth.
Find you to turn it off by camera. I lost. Oh, here we go. I think I have to stop sharing for a minute. Oh my goodness.
You
We
actually
already didn't have
sound
time.
okay now. So
Okay.
maybe keep going.
Maybe it
and
was a weird thing. Okay.
yeah.
Am I still sharing the presentation?
Yeah,
Yeah.
you just got to make that full screen again.
Yep. Okay. So you already saw how chemical properties affects transport and soil properties affect it. Ian also mentioned this. You have sorption to the solids, you have biotransformation.
We're having trouble hearing you again.
Can you hear me now?
Yes.
Okay. I don't know if everybody's having trouble. So I'm going to show you some quick cases. So this is the dedicated disposal site, and this is a little different than the norm, but I really want to show you the data because it shows the value of biosolids. So this is 1 year after the last application, 40 years of application. Look at the carbon content that's built up in that soil. This is from the West Coast. The soil has very little carbon content in general on the West Coast. You've got this really rich 2 feet of soil with really great carbon. If we didn't have the PFAS issues, which those are lessening now, biosolids, it's just one example of how valuable they are. You can see the orange. These are all long chain. Dark orange and light orange are all long chain sulfonates and carboxylates. That's what's retained in the upper 2 feet of the soil. If you look to the right, I'm showing you the percent distribution of different classes within each depth, and I'm showing you the last biosolid that was applied. And so what you see in the last biosolid that was applied is all the grays and dark grays. Those are all precursors. They are not on the EPA 40 list. But what you see within 1 year, when we take the soil core, most of them, except for the 3M electrochemically derived precursors, this medium gray, have degraded into the persistent acids that I talked about. And you again see that as we increase with depth, we see mobility of the short chain. And actually in the groundwater monitoring well, not a drinking water well, the only the only PFAS that exceeded EPA limits, even when we had 6 we were monitoring, was PFOA. And it was still only at 39 parts per trillion, which, yes, that's 10 times higher than the 4 we target now, but it's half the concentration that was the original guidelines. So that's pretty encouraging, just in general. Another site in Virginia where we have 3 soil types, all at the same site, all being managed in a similar way. And what we call the Acrodil reference is just the soil, the darker gray fields where we did not apply biosolids in 2023. And I'm going to talk about what we see prior to that 23 application. So we had low to high permeability. It was all Class B until they moved to Class A in 2023 after they implemented a thermal hydrolysis process to achieve Class A biosolids. And I think it's important to note in the 2023 biosolids, almost everything was what we've referred to as DIPAPs that are not on the EPA 40 list. So you can have a total PFAS concentration from the EPA 40 list that's small, but have this very large amount of PFAS present, but you can see very little sulfonic acid. So the ones that are our biggest concern, PFAS, PFOA, they're really coming down. And I have to say that DC water has really brought their concentrations to very low levels. So if we look at the soil cores, you'll see very consistent with some of the things Ian talked about. All these oranges are the long chain PFAS. Dark orange is the PFAS category, and the lighter orange is the PFOA category. And you can see that is what dominates in the soil profile. I also want to tell you that this site, these cores are from the site that was 9 years after the last PFAS application. So almost a decade, no biosolids applied for a decade. Yes, it's in rainwater, and Chris brought that up, but nothing from biosolids. But yet you still see this very strong long chain legacy PFAS signature. And when Chris mentioned, when PFAS were regulated out of the pans, it was more regulation than that. They were almost regulated out of all use. And so we had a good response by our blood levels lowering. So you can just see long chain PFAS persist. And in this case, it tends to be the silty clay materials that helps to hold things in place. So we call it kind of a textural driven process at this more humid, rainy climate site near the coast. And after biosolids were applied, we took cores 1 year later. You couldn't tell any difference because one biosolid application is not going to look any different on a legacy site. And the monitoring wells, almost all the wells had total PFAS less than 20 parts per trillion, nothing really exceeding EPA's drinking water limit.
Linda, I think your audio might be cutting out again.
Let's see. I don't really want to stop.
Yep.
Can you?
That's okay. I'm just letting you know if it kind of.
Okay. It was happening with Chris.
We did miss your last few. I think a lot of that last slide there.
Okay, so what I was trying to tell you is important that even after all these years of regular agronomic applications, the monitoring wells in almost all the cases had very low PFAS levels. Exceptions were wells close to a lake that we think are impacted by things discharged into the lake. In this site, every 5 years, they apply biosolids one time and they rotate the field so that they're really only doing applications once every 5 years. What I'm showing you here is pre and post the last application in 2020. So prior to the 2023 application on one of the sites. And you can see basically the important part, it's all long chain PFAS. Again, there's very little of anything else that's hanging out in that surface soil. So again, Chris mentioned this, and I think it's important to realize that the rainwater signature for PFAS, the PFAS signature in the rainwater at the Virginia site, PFAS was at or above EPA drinking water limits. And when we look at forest soils that had never had any PFAS applied, we see that signature with lots of PFOA and PFAS building up in the surface soil. And Chris exemplified that very well for another area. So this is really important. And this could be from rainfall, and you could have aerosols from the lake that's highly contaminated with PFAS ending up in the air and raining down, military base and airport within a small radius. So we have to think about that at every site. When we think about background, it really varies. My one concern with these legacy PFAS hanging out in the soil is runoff events. So with high runoff events, the PFAS loads can be high. This is an example of what we saw in the runoff at one of our sites, really high long chain. Not surprising, that's what's hanging out in the surface soils. And then they can get into lakes and ponds, and I'm most concerned with closed body ponds that might be on farms. This example is from this example is from Indiana, a site that had not had biosolids for 25 years. But prior to that, it was legacy biosolids, where we had no control of PFAS coming into our products, our processes in our plants. And, this farmer's not happy because one large wide-mouth bass would be his PFAS load for his life that he should get. Cattle drinking water from these contaminated sites can end up with milk that's not acceptable. This milk was okay, but milk that would not be acceptable, and we only have Maine guidance for that. So that is a concern to me for the legacy sites. We need to control this runoff because we need to control what gets in water bodies. What time is it? Okay, 5 minutes. I gotta hurry. So we have a lot of sites where we had lysimeters, which collects pore water at different depths. And I just want to show you a comparison between a first-time application of biosolids on a site that had never gotten any on the left. On the right is where a site had been given about every 12 to 15 months an annual agronomic rate where they grew corn and soybean. And what you can see on the left first time event, mostly what shows up in the lysimeters at 2 feet and 4 feet are just your short chain carboxylates. They're not regulated. They're less of a concern. In the legacy site, you still see mostly short chains at 2 feet. That's the little red checkerboard. But you do see in the deeper profile, you do see some of the long chain sulfonates and carboxylates, and even some of those electrochemically derived intermediates. It's a legacy. And if you look at the soil profile, again, and Ian mentioned this, look at what's in the surface soil. These are all this is total PFAS. And there was 18 that were detected of the 70-ish that we measured. The total is less than about a half a part per billion. And so that's why a single application is really not doing anything. And it was mostly short chain carboxylates and short chain sulfonates. Sometimes we see long chain carboxylates. It's the PFOA that you're seeing. But in the long-term site, in the deeper profiles, you start to see some of the legacy. It's all legacy. And then just one example, because Chris mentioned it, of blending. We did, this was also a site in Virginia where they blended with mulch and biosolids and composted them together. And PFAS was highly retained in the soil and did not get into that 15-centimeter lysimeter in the blend, even though we had to apply more of it to achieve the same agronomic rate based on nitrogen. I'm going to show you a few crop uptake and we'll be done. This is in that 5-year cycle West Coast example, and I'm showing you the last time biosolids were applied on each of those cycles. You can see that in our last time it was applied in 2018, 2019, the only thing we're really seeing is the short chain. The solids can vary over time too. It's surprising to see in the oats. We saw in the last for ones that were applied later, 21, 22, we did see quite a bit of PFAS, and you still get PFAS coming into plants through landfill leachate and actually invasion into underground combined sewer overflows that are coming from like Air Force contaminated groundwater. And I want to show you our soybean greenhouse study that I think I'm only going to just show you the beans. We did lots of part of the plants. I'm showing you the beans and the leaves. What's most important, this soil was an industrially impacted soil, very similar to the one in Maine, but even worse, with almost 3,000 parts per billion PFAS. Most of it was either PFOS or the precursor to PFOS. In the bean, there's no PFAS. It was almost all short chain carboxylates. And we think it's because they are transported through non-specific substrate transporters. And important, the high concentrations in the bean is only because it was a greenhouse pot that we didn't allow leachate. When we looked at the Virginia site, just few parts per billion, only the PFBA, the C4 and C5, and in the pod around the bean, we saw a little bit of PFBS. But even though you have, you saw all the PFAS that was present in the soil profile, not showing up in the beans. Soybeans are safe, even on highly contaminated soils. When we looked at feed grass, and this was using soils from Maine, we see that when we used a different weight wood ash that we mixed in with the soil. And you can see that as we increase wood ash content, we saw a decrease in the translocation factor of PFAS into the grass. This is feed grass for cattle, and all of it was significant. So this was encouraging. So we were doing this in Maine in the field. Well, unfortunately, in the field, we didn't quite have the same lovely results. So we had the similar soil. You see a lot of PFAS and ETFSA. They applied the thing, the char. It got tilled in, and we had both a biochar, a wood-based biochar, and a wood-based wood ash that cost about 30 times less. And you'll see that in our first two harvests of both years, we had sorbent mitigation, but not in the second two harvests. We think it's weather related because before the second two harvests, it was very hot and dry. And wood ash and wood biochar will hold water in the soil zone. So we think this might have been, negated some of the mitigation effects. So we're going to continue that work and expand it and include modeling efforts to better understand the role of moisture and weather. And, lastly, good because they don't get offload. It's a plant physiology thing that I don't have time to talk about, but it tells us there are things we can grow. We just can't use silage from corn that's grown on PFAS contaminated lands. And we do have to be mindful that it's not just about biosolids. And Chris mentioned this. I'm finding problems on
Unfortunately, Linda, we're losing a bit of your audio here. I know this is, I think your last or penultimate slide here, but you are frozen, and we are at time. But I'd love to just try to get through a few quick questions here. Yeah, if you want to go ahead and do your takeaway slide, go ahead.
it's there. It's all right. You can read it. I gave you takeaways at first.
Yeah, I'm sorry. We are having a tough time, but we will make these slides available as well as the recording. But thank you again, Chris, Dr. Pepper, and Dr. Lee for these great presentations. I will go through a few of these questions really quickly here. If everyone presenting here can stay on for a few minutes just to get through some of these. We had a lot and much appreciated. So let's see, Christina, Chris, this is a question from Christina. She said, could you share with me the data showing incinerators can send PFAS into the exhaust and therefore into the air and the precipitation? You gave examples of Maryland, Virginia. I'm particularly interested in New York, but would love to see any US data. Obviously, you can't go into that in this short time, but if you can, Chris, provide any guidance on where she might be able to find that.
Yeah, I was responding in the questions, and I'll send you what I have. It's largely has to do with the temperatures and the studies that oftentimes there's problems with the detection limit in those studies. They have very high detection limits, and then they show non-detects, and they say, all right, it's gone, but you don't really know what they are at the lower levels. And there are some difficulties in air samples. There are some modern high temperature incinerators who have shown or are claiming destruction. I can send you what I have, though.
Great, thank you. Question from Darren. For the soil sampling depth, was the sample thickness from 0 to 1 foot, 1 to 3 foot, and 3 to 6 foot, or much narrow thickness at those depths? That's for you, Ian.
Yeah, the surface soils were 0 to 1 foot, and then for 3 foot, we'd go 6 inches above and 6 inches below 3 feet. And similarly for 6 feet, 6 inches above and 6 inches below.
Question for you also. You mentioned that 1 or 2 sites had higher PFAS and biosolids due to the landfill leachate impact on the wastewater treatment plant. Did you look at leachate contributions, i.e. flow and PFAS concentrations?
We had a sample of leachate that was high in PFAS, but certainly nothing with flow rates. That's kind of outside the scope of what we were looking at. But it seemed to be a nice correlation between, leachate landfill and bingo, the concentrations of PFAS skyrocket. It's pretty well known that landfill's leachate is loaded with PFAS.
Another question for you. What is the application rates that apply to low biosolids and high biosolids?
Not quite sure I understand the questions, but I would guess that mostly people were applying in agronomic rates, maybe 2 tons per acre, I would guess. But we were just getting the lifetime loading rates from these sites, and you can imagine pretty hard to dig that material up, going back all those years.
A question, kind of a philosophical question, is zero PFAS application realistic? How do we get to zero? I know that's kind of a larger question than we maybe have space for here, but if you
who's that from?
that was during your presentation, Dr. Pepper, but I think anyone can answer that, really. I think Chris, you're unmuted.
Chris is anxious, I can tell.
Yeah, I mean, I think it is unrealistic, especially since there are studies like the New York study that shows that anything up to 3 parts per billion is quote unquote naturally occurring or sort of ambient levels, background levels. So 0 is, I mean, that just means you can't farm anything, even if it's never received biosolids. So my humble opinion is no, that's not realistic.
A question, have you looked into PFAS analysis of air emissions?
I haven't.
That might be directed to me because I made the comments about the incinerators, or was it air emissions from fields? I'm not sure exactly what it was, but same answer applies to the incinerator question earlier. I have some things that I can pass along. I don't know that anybody's looked at transpiration off of fields from plants. Maybe that's what they're referring to. Linda, are you familiar with anything related?
What was the question? I was answering a bunch of questions in the chat.
I was, has anybody looked at air emissions measuring? And I answered the question about from incinerators, but they may be talking about transpiration from plants. I don't know if that's even possible, but nope, Linda looks frozen.
Sure. Oh, again, can you hear me now?
Yes.
Yeah.
Okay. What I was going to say is I have not seen that directly for PFAS. I've seen it mostly for chlorinated solvents, which are pretty volatile. So I think that it would be a bigger concern would be dust inhalation more than coming off. When you say plants, you mean crop plants.
That's what I
meant.
That is what I meant. I'm not sure that's what the questioner meant, but
yeah. But I think it does come off. I think aerosol basins and during composting and all that. There's evidence that we are losing stuff to the air or aerosols during that process. But crop plants, I don't think so.
Easy question for you, Dr. Pepper. Darren was asking, is the training video available online or via share?
Yeah, how do you want to handle that, April? I could send the video to you, or you can have people email me directly. Either way.
Yeah, if it's something that will fit in an email or a link,
well,
then we will
I'll
send
get it
a roundup.
to you.
Yeah, we'll send a roundup of resources and we can include that. Question, has anyone compared biosolids application to cropland with cattle manure application?
I answered in there. I think there might be, I was going to say that in general, manure has very low PFAS if you can even measure it, unless it's a farm that's getting PFAS contaminated feed, or they have a PFAS contaminated farm, and then they kind of have an overall bigger problem anyway. But I don't know if so it would be kind of hard for most cases to really probably track PFAS very easily from manure applied farms. I'm trying to think, and I don't think anybody's trying to do it even in small plots right now. But in general, I haven't seen manure be too much of a problem except for those, highly contaminated farms.
Okay. Let's see here. Keep having things coming in here. Question. Let's see. What? I think this was for you, Ian. What hydrophobic properties of biosolids are known in the national study? More generally, what surface/material properties, if any, are available for the materials supplied?
I saw that question and I got to admit, I'm stumped. I'm not familiar with the hydrophobic properties of biosolids. Chris, can you help out at all?
I think maybe they're talking about carbon content and salts and all these different things, but it changes over the years and it'll change depending on where they're getting their biosolids. And something else no one asked is it broadcasted? Is it distant? Is it subsurface injected? All those things can matter a little bit, but not so much.
And the short answer to the question is no. The only thing we looked at in the biosolids was the PFAS concentration.
Question, are we aware of any studies looking into reed drying beds for biosolids and potential uptake into the reeds? Curious to see if there is potential to continue this treatment technology to increase uptake from biosolids and side stream treatment of filtrate returns.
I haven't done that.
So you're asking if you mean in the wet dry biosolid drying beds, if you might be basically looking at a phytoremediation, I think, if that's the question. I suppose it has potential, but I wonder, I'm not sure how much potential unless you have a very aqueous slurry, because people right now, people want to talk about phytoremediation, but the amount of mass, even though it's problematic when it goes in.
Yep, losing you again here. Okay, we'll keep rolling here. Sorry, they keep coming in here, and let's see. Does information on legacy PFAS concentrations in biosolids exist? What were past concentrations in biosolids?
There's a
I
paper.
did have.
Yeah, go ahead, Linda.
Go ahead, Ian. No, you go ahead.
I was going to say Ralph Haldon published a paper, I'm blanking on me, probably 10 years ago now, looking at concentrations of PFAS around, I think, the period 2000 to 2005. Are you familiar with that one, Linda?
Yeah, but that's still old. I was going to share.
That's what he wanted.
Oh, I thought he wanted to know between there and now.
Well, they were higher then.
Obviously. So I was gonna, I had it in my, I didn't know if you're sending out the slides, but
Oh, geez. Sorry, we're still having trouble with your audio.
okay, so you can see
there we
this
go.
range. So a lot of them drop below limits of detection.
Still having trouble hearing you. We might have to maybe if there's something you want to write up later, we can come back to that. Yeah, not hearing you, unfortunately. Question, what is the definition of safe? Does that mean it meets health advisory levels?
What's the definition of what?
Safe.
Oh,
I responded in the comment about it. It's always relative to MCLs because that's all we have. And just don't confuse soil concentrations with water concentrations. Soil and biosolids are in parts per billion. Water concentrations are in parts per trillion. The regulatory things right now are for water, unless you're in states that are at least making decisions about applying certain levels or not. So
Also, usually we do not comment on whether something is safe or unsafe. Rather, the best approach is risk assessment, generate a risk, and then you let other people determine whether they think that's safe or not.
and I apologize that I lost my desktop right before this and they couldn't fix it. They have to send somebody. So I had to switch to my laptop, and can't trust wireless on your own campus.
Yeah, well, we had our own technical difficulties, even though I had lit a candle to Murphy for protection, and Murphy's Law always pops up, when you have a 500 people turning into something.
April, I'm telling you, Zoom is better than Teams. There's always issues with Teams.
Yeah, this is DC Water's platform, but for the next time, maybe we will just buy a month of Zoom to do it that way. I quickly, I think maybe one more here. This is from John. Chris is familiar with loading rates research at 100 pounds per acre versus tons, meaning fertilizer rates versus land application / amendment rates. Any renewed interest to develop this market?
I'm not sure I understand the question.
While you're thinking about it, I think we need to really push for creating high nitrogen. We think about a nitrogen PFAS ratio, because if you apply based on nitrogen. And so even things like malorganite that back in 2018 had very high PFAS compared to other commercially available bagged biosolids, the nitrogen was so high that if you applied it based on nitrogen rates, you applied the lowest amount of PFAS across all the commercially available products, even the ones that were not biosolid based. So I think we should be really trying to enrich nitrogen in our biosolids while we get people to stop using PFAS.
There we go.
I think I understand the question
Okay.
now that was asked. The answer is yes. So I think that what he is referring to is a dried product. And of course, we're always interested in diversifying our product lines. So yes.
I think we'll do this last question. Any news on whether different states will legislate on quantity of PFAS and biosolids, or federal regulation for land application?
From what
It's
I've
already
seen,
happening.
yeah, they're blanket bans. Like Connecticut introduced a ban by sticking a single sentence into the legislature late at night, just before the thing was introduced. And again, it's not, less than a certain amount. It's any, and it's banned. That's what I've seen. And Linda, Chris, you seen anything else?
There's a lot of bills out there right now and most of them are the bills that are out there that are not for banning are kind of following Michigan's guidance.
Yeah, Michigan makes an attempt to make a distinction between municipal biosolids and industrially impacted biosolids. And several states are following suit. And then there are those who are doing what Ian described as well, which is a outright ban.
Actually, there's one last question that came in. I think is a nice bookend to that, which is, how do we address public perception about PFAS and biosolids? I think that's a good place to end.
Yeah, I mean, we've been very proactive about getting out and talking to our customers, and a lot of the stories that come out make it seem like we have astronomically high levels in our biosolids, and that's just simply not true. So what we try and do is compare it to the levels in the products that we use every day. We show people that most of it's coming from our homes, and then we really should try and get together with all of the generators in the country and come up with some sort of a plan to educate our generators, the people, because if the solution to this is source control, it is to get it off of our shelves, and we have access to every person who is hooked up to the sewers through our billing system, and there are organizations that help get us all together and do things. So if we presented a unified front and presented a message that states could then give to the sewer users, we could probably make a real difference. But just being honest about what's in the biosolids and following the research. I mean, we do research all the time because I think that it'll support our belief that what we are doing is safe, and B, if we find out something that contradicts that, we want to know that too. So we're all concerned about PFAS. My advice is just to be transparent.
I've always found that the general public, if you can show them that there is quality research on a given issue, that reassures them much more so than someone just saying, it's safe. If you've got data to show that the levels are low, that's the way to go. So more research, and I think there's a number of studies that are ongoing or about to finish that can provide that data.
I just wanted to make.
Oh,
No.
unfortunately, Linda, you are not audible. So I'm afraid we're gonna have to wrap it up here. Thank you, everybody, especially for sticking around. And to our presenters. And as I mentioned, we will be sending out a recording probably Monday along with the slides. I'll also include a link to a webinar that we have coming up on Tuesday, if you haven't already registered. That's going to be on best practices in stormwater management. So we invite you to sign up for that as well. And thank you again, and have a great rest of your day.
Bye-bye.